again, I got a note the other day from somebody asking how to calculate the stresses in a spherical pressure vessel. Now this person didn't tell me whether he or she was interested in a thick wall or a thin wall pressure vessel. I'm going to guess it was a thin wall pressure vessel. That's the ones we're usually interested in. So this is going to be how to calculate the stresses in a thin wall spherical pressure vessel. So let's start by saying, what does a thin wall spherical pressure vessel look like? Well, those of you who've seen this, seen these videos before, I used this ball before. It was Earth in one of the orbital videos. So this is pretty much a thin wall spherical pressure vessel. Now, is there a lot of pressure in it? No, not really. You know, I can sit here and squish it, so there's not a lot in there, but there's enough. The interior pressure is higher than the exterior pressure, outside pressure, so it's spherical. The wall is very thin compared to the diameter. Now, one of the things you'll note if you start doing Google searches is that there's no one definition of a thin wall pressure vessel. What constitutes a thin wall pressure vessel? In the most general terms, it means the diameter is large compared to the wall thickness. Well, what's large mean? When we teach here, we usually use the number 20. If the diameter is 20 times the wall thickness, it is considered a thin wall pressure vessel. That's not the only number floating around out there. I just looked it up a few minutes ago and found 10. I suspect there's probably more, but the big idea is that the diameter is large compared to the wall thickness. Okay? Now the expression for a thin wall, spherical thin wall pressure vessel looks like this. Okay, it's very simple. That's pressure. That's the interior pressure on the pressure vessel. And that's actually the pressure reference to the outside. Okay, and that's the mean diameter. Force is just a number, and T is the thickness. Well, it's nice to have that expression, but if we don't know where it comes from, we're maybe not catching the whole point here. When I see my students just start flipping through a book looking for an equation without any concern about where it came from or where it's applicable, I worry. So let's maybe see where this comes from. It's very simple. Let's draw a section of a sphere. All right, that's a sphere that's been cut in two. Okay, that's this just sliced in two. Okay. And so we've got pressure acting on, a force acting on that wall right there. And we're going to have the pressure go this way, okay, because of our fictitious cut there. And here's the area over which that pressure acts. Okay, and I'll call that big A. We're going to use little a here in a minute too, and that'll be something different. Now, I know it's really tempting to look at the pressure that way, and I suppose you could. But if you do it this way, it's going to be a lot more complicated. We're looking at the force acting across that fictitious cut, and that really does go one direction. So we're not going to use that. Okay, yes, there is pressure on the outside, and that's what keeps the pressure vessel in tension. But this is an easier way to derive the equation. Okay, so let's see here. The normal stress is just force over area. Last I checked, I think that's still true. Well, force is pressure times area. Okay. Well, pressure is going to be given. Now the area is going to be pi over 4 mean diameter squared. Okay. And if you want to put pi r squared, that's fine too. It's just a different way of saying the same thing. And I'm not going to call that big A. I want to call this little a, and I'll even put a W there. That's the area of the wall. Okay. Now, if you want to see what wall area looks like, here's a little section out of that sphere. This is right at the cut. This is right here. Okay. There's the wall. This is the inner diameter, and the middle of it there, that's the mean diameter. Now, which one do we use? You could use either one. Now, if you want to track interior diameter and mean diameter, you can. If you want to replace that with interior diameter, that's completely okay. By doing it this way, by calculating pressure using the mean diameter and then calculating the area using the mean diameter, things start canceling out and you get a much simpler expression. the idea of saying that the wall is very thin compared to the diameter means this is almost zero, not quite, but pretty close compared to the diameter. So what we do is when we calculate this area, acting right there, we actually use mean diameter, even though it's more correct to say interior diameter, right? The difference you get between doing those is so small, it's negligible, and it makes the expression simpler. Okay, so if you're wondering why that's not interior diameter, that's a fair question. We do it this way to make it simpler. Right, so there's force. Now the area of the wall, easiest way to do that is circumference times the thickness. So pi mean diameter times thickness. And what we're doing here is we're saying, well, if we took a sheet of metal that had this length, pi times the mean diameter, and it had that thickness, okay, we could take that piece of metal and bend it into a circle, and we get this. So if you want to calculate the area by calculating the area of the outside of the outer diameter minus the area calculated with the inner diameter, you can, and you'll get this. Okay? So the other way to do it is say, well, if I was going to make a thin wall pressure vessel, I could take a flat sheet of steel with those dimensions, that width and that thickness, bend them into a circle, I'd get that, there's my area. So that's where that comes from. I need some real estate here, so I'll clear that out. Okay, so to get to there, let's see. Let's find stress using what we know now. P times pi over d, or pi over 4 mean diameter squared. Okay, that's the force. Divide by that area. Well, pi mean diameter t. Well, looks like we ought to be able to do some simplifying, right? I think so. So that cancels out, and that cancels out. And so now we're going to get pi times mean diameter over 4t. Let's try that one more time. One more time. All right, you can tell I'm having a long day here. Sorry. P times mean diameter 4t. There you go. Boy, I had to work for that one, but there it is. Just in case you think you guys are the only ones that make mistakes, professors make mistakes too. The difference is we tend to make them in private where nobody else sees them. So by the time we get in front of a class, we've usually worked it all out. We have just as many problems as you do, and that's typically why we have partial credit on tests. At least that's why I do it. That and that are obviously the same thing. So there's your expression. There's where it comes from. Let's throw some numbers in here and see what happens. Okay? If you're okay with that, I'll erase this and I'll put some representative numbers in here for us. Okay. Well, let's calculate the normal stress if P is 100 atmospheres. So it's 100 times the pressure of the atmosphere, and at sea level it's 101.3 kilopascals on average. Okay, that's that's pressure, atmospheric pressure in the metric system. If you insist on doing it in the English system, it's 14.7 psi, pretty much. Okay. So that's 1.013 times, I gotta check this out, make sure I do it right, 10 to the 7th. Okay, and always go back to your base units. Always go back to newtons, kilograms, and meters and seconds. If you try to work everything in kilograms, kilopascals, you're going to wind up making more mistakes than you should. So there's that. All right, diameter, which is mean diameter, that's going to be 2 meters. And thickness, we're going to make that be 0.050 meters, and that's 50 millimeters. So American guys, that's basically 2 inches, pretty much. Okay, so I work this out. I'm going to get, okay, PDM. So 101.013 times 10 to the 7th pascals times dm, so that's 2 meters, and over 4 times 0.050 meters. Well, now are the units going to work out? Yeah, meters cancel out, you're going to get pascals. There you go. Stresses in pascals, and I get, that works out to 101.3 megapascals. Now, I originally worked this out in base units and only then converted it to megapascals, because this is what's in all the charts and all the textbooks. Now, this is actually kind of high for stresses in a pressure vessel if you're using kind of a low grade, 1010, 1018 kind of steel. That would give you a safety factor that's maybe a little lower than you'd want. So, but we now know how to fix this. If I've got an expression for my stress in my spherical pressure vessel here, if I want the stresses to go down, I can make the diameter smaller or the thickness bigger. So there you go. There is normal stresses in a thin wall spherical pressure vessel. Hope this helps, and I'll see you next time.